Hi, my name is Richard Pymar. I'm the Program Director for the MSc in Applied Statistics at Birkbeck. So I've put together this short video to demonstrate the format of my lectures next year, and also to give you some information about the content of the first year of the part-time mode for this program. So there are two modules that make up the first year of the part-time mode. One is statistical analysis, and the other is probability and stochastic modeling. So I teach on the second of these two modules, the probability and stochastic modeling module. And in the first term, we will be looking at some probability theory, which underpins statistics. So we'll look at probability theory and also distribution theory. So we'll be talking about random variables, distribution functions of pairs and collections of random variables, and we'll also see some convergence results for sequences of random variables. So you might have come across the central limit theorem and the law of large numbers, for example. So some convergence results. We'll have a few lectures on Markov chains. So Markov chains are stochastic or random processes. So these are a collection of random variables indexed by time, and they have a certain property called the Markov property. And what that essentially means is that what the process does one step into the future only depends on the state of the process now. So it doesn't depend on the state of the process in the past. And then there'll be some lectures on statistical inference. So we'll talk about sufficiency, likelihood, estimation, unbiased estimation in particular. And there'll also be a lecture on hypothesis testing, and then an introduction to Bayesian statistics. So this is going to be on statistical inference. And the majority of the second term will be focused on time series. So time series, this refers to a set of observations, each being recorded at a specific moment in time. So what I want to talk about in this video is a bit of the content that we'll cover on Markov chains. So Markov chains, they're very useful. So they have applications in, for example, Markov chain Monte Carlo. So this is where you have a complicated, but perhaps very high dimensional distribution that you want to sample from. And Markov chains give you a way of sampling from that distribution. So Markov chains are an example of a stochastic process. And stochastic processes are, in general, very useful, for example, in finance to model the price of a stock. And also they can be used as a model for time series. So let's think about one of the simplest Markov chains that we can have. And this is going to be obtained by just repeatedly tossing a fair coin. Okay, so we toss a fair coin. Then there's two possible outcomes, heads or tails. And let's say if we get a heads, we're going to assign value 1. And if we get tails, we're going to assign value -1. And so we can think about what a possible sequence of outcomes of this experiment is. So if here on the x-axis we have time, and then on the y-axis this could be 1 here, and this is -1. So at time 1 we toss the coin for the first time, and let's say we get heads, so that's going to be a +1. And at time 2 we toss again, and maybe we get heads again. At time 3 maybe we get -1, maybe -1 again, and -1 again, and so on. And actually this is a Markov chain, but we can get another Markov chain by summing this Markov chain. So what do I mean? Well, okay, let's again have time on the x-axis. So what I'm going to do is just to get the value of this new Markov chain at time n, I'm going to sum this previous Markov chain up to time n. Okay, so at time 0 we're at 0. At time 1 we had heads, so that gives us a +1. At let's say this here is 1. At time 2 we got another 1, so we're going to add it. So now we get 2. At time 3 we have a -1, so adding that gives us 1 again. And then at time 4 we have a -1, so we go down to here. At time 5 we also have a -1, so we go down to here. And we can even connect these dots up. Okay, so we get something like that. And we can think about running this process even longer in time. And it will give us some trajectory which takes values on the integers, the positive and the negative integers. And this is a Markov chain. Actually, it's called the symmetric random walk on Z, or on the integers. So this is called the symmetric random walk on Z. Symmetric because we jump up with probability half and down with probability half. So a question that we could think about is, if we start from 0, as we do here, what is the probability that we return to 0? Right, so another way of phrasing that is, are we guaranteed to return to 0 or not? So question, are we guaranteed to return to 0, assuming we start at 0? And this question of whether random walks are guaranteed to return to where they start to, actually this is a property known as recurrence. So we say that a random walk is recurrent if it has this property that it's guaranteed to return to its starting state. So back in the early 1900s, the mathematician Polya was walking through a park, and he kept bumping into the same couple over and over again. And he presumed that both he and this couple were moving as random walkers, and he wanted to know, well, what is the probability of this actually happening? And so this led to Polya's theorem, and this is a theorem about random walks on Z, but also on higher dimensional versions of Z. So we could take Z squared, which is just the lattice or the grid, Z cubed, which is a 3-dimensional lattice, and in fact even higher dimensions as well, it can be defined. And Polya's theorem says that the symmetric random walk on the d-dimensional grid or lattice, Z to the power of d, is recurrent. And so again, that means that the walk is guaranteed to return to where it starts from, if and only if d is equal to 1 or 2. So in dimensions higher than 2, actually there is a positive chance that the walk does not return to 0. And actually what that means is there will be a time after which the walk never returns to 0. Okay, so in the lectures we'll talk about how we can prove this using a path counting arguments, or look at the various trajectories that the random walk can take. But what I want to show you now is an alternative proof for d equals 1. So what I want to show is, why is it true that when d is 1, so we look at the walk that we started to draw a possible trajectory of here, so why is it true that with probability 1, if we start from 0, we're guaranteed to return to 0? So what we can do is, we can, let's say that we're going to define pi to be the probability that that we return to 0 starting from I. And let's make another representation of this Markov chain. So let's say this is 0, 1, 2, 3, and so on, -1, -2, and so on. So if we start from 0, then with probability a half, we jump to +1. With probability half, we jump to -1. And that's the same from every state. So from 1, also with probability half, we jump up by 1 to 2, and with probability half, we jump down by 1 to 0. So let's consider, instead of looking at this process, let's consider a process which looks at the distance to 0. So let's say here this is 0, so we're looking at the distance to 0. So if we start at 0 up here, then the distance is 0, and we're guaranteed to jump to distance 1. Then from 1, with probability half, the distance drops down to 0, or it goes up to 2. And also from minus 1, with probability half, the distance drops down to 0, or it goes up to 2. So with a half, we jump down to 0, and with a half, we jump up to 2. And then from 2, it's the same in the sense that with probability half, we jump up to 3, and with probability half, we jump down to 1. Okay, so this probability Pi, what we're interested in, well, starting from 0, we definitely jump to 1, so what we want is P1. And I claim that it's equal to 1. So why is that true? Well, a trick that we can do is we can think about what happens if we look at one step of the process. So P1 is the probability that we return to 0 starting from 1. Well, starting from 1, with probability half, we go to 0. So we've definitely returned. Or, with probability half, we go to state 2. And then we're looking at what's the probability from 2 that we return to 0. And that's just P2. Okay, and then we can think about P2. Well, we could write this as a half P1 plus half P3. But actually, there's something a bit cleverer we can do. So to go from 2 to 0, we have to pass through 1. So the probability starting from 2 that we return to 0 is actually the probability that starting from 2 we return to 1. And then starting from 1, we have to return to 0. Well, starting from 1 going to 0, that's P1. And what is the probability starting from 2 that we go to 1? Actually, that's the same as starting from 1 we go to 0, because we have this infinite set of possible states that this process can take, right? 0, 1, 2, 3, 4, and it goes on. So this is also P1. So this is just P1 squared. Okay, and then if we plug this value of P2 into the equation above, we just get a quadratic. So we get that P1 is a half plus a half P1 squared. So multiplying by 2 and rearranging, we get that P1 squared minus 2P1 plus 1 is equal to 0. And this has just a repeated solution, which is that P1 equals 1. Okay, so that actually exactly tells us that started from 0, what is the probability that we return to 0? That's just equal to 1. Okay, so this is how my lectures will look next year. I'm just one of several lecturers teaching on the MSc in Applied Statistics, so it may differ from lecturer to lecturer. But I hope that you enjoyed this taster video, and I also hope to see you in the next academic year.